we've seen that the satisfiability problem is NP-complete, and now that we have one NP-complete problem, we can, let's say, a bit easier, we can prove NP-completeness for other problems a bit easier. It's a bit easier than for the first problem. So this is an overview over NP-complete problems. Actually, there are a lot of NP-complete problems, but we'll have a look at only a small sample. The first problem we know to be NP-complete was the satisfiability problem for propositional logic. So here we had a formula like this one here, A and A implies B, and B or something, and we'd like to know whether this formula was satisfiable or not. To prove NP-completeness for other problems, we still use polynomial time reductions, but now we reduce the satisfiability problem to these problems. And the first reduction that's usually done is that we restrict the formulas we allow, and we show that 3-set is NP-complete. 3-set, it's still satisfiability for propositional logic, but here we require the formulas to be in conjunctive normal form and have exactly 3 literals in each clause. So the formulas that are allowed here are in conjunctive normal form, and they look like this. We have A or not B or C, and A or B or not C or something. These are the formulas that are allowed here, and this is in conjunctive normal form, And 3-set is because we have 3 literals in each clause. This here is a clause. Now, there are other problems that are NP-complete. For example, the so-called rucksack problem. In this problem, you have a set of numbers from A1 to AN, which are weights. And you would like to put the weights in your rucksack, and you have a capacity, let's call it K, weights, the capacity. And the question is, what can you actually pack? So what you use is, what you would like to know is there a subset I of the items that would fit, so that the sum of the weights is the capacity of the rucksack. This problem is NP-complete as well. There are other problems that look completely different, like graph colorability. Here you have a graph and a number of colors, and you would like to know whether you can actually color the graph. How does it work? You have a graph like this. And now you would like to apply colors such that adjacent nodes have different colors. So if you start with blue here, color this one blue, then you can add a red maybe here. Now that you have red here, you can reuse the blue, these two, And then you can reuse the red here. So actually, this graph here would be two colorable. Two colors would be sufficient. And the question is, how many colors do you need? Is it possible to color a graph with a certain number of colors? That question is also NP complete. Okay, there are more graph-related problems. We have, for example, the clicker problem. Clicker problem is the problem given a graph, this one here, and clicker is a subgraph that's complete. The idea is the nodes are persons, and the edges indicate a relationship. So, for example, this group here forms a clicker because everybody knows everybody. So this is a clicker of size 3. And in general, the question of this problem would be, given a graph and a number k, is there a click of this size in the graph? Even more graph problems. Hamilton circle. Hamilton circle is the idea you have a graph and you would like to do a round trip. And the question is there a round trip that visits every node exactly once? In this case, there's apparently, and the question is there a Hamilton circle in a graph? And quite related to this is the so-called traveling salesman problem. This traveling salesman problem, you have a matrix of distances, and you would like to know whether there is a round trip visiting all the nodes that has an upper bound of the length of the trip that satisfies a given upper bound for the trip. And these problems, for example, are very important for logistics. If you want to plan routes for your fleet or something, then you end up with these kind of problems. So they are all NP complete. That means that we don't know whether an efficient algorithm exists or whether we have to use heuristics.